Imagine an orchestra warming up. Two musicians sit side by side, attempting to play the exact same note, but one instrument is slightly out of tune. Instead of a smooth, harmonious blend, you hear a distinct, irritating throb. It's a pulsing volume that swells and dips in a regular rhythm. In physics, we formally define this waxing and waning of sound intensity as beats. It's a strange paradox. Adding two continuous, smooth notes together results in a broken, stuttering sound. The cause of this phenomenon is found in the air between the instruments. As both sound sources push on the atmosphere, they create invisible ripples of pressure that collide and overlap. The auditory throb is a physical collision of waves in space, governed by the principle of superposition. Superposition dictates that when two waves occupy the same space, their displacements add together algebraically. Consider two waves at 11 and 9 Hz. When occupying the same space, their displacements add together. Where peaks align, constructive interference creates a massive green spike. Differing frequencies eventually drift out of sync, canceling each other via destructive interference into moments of silence. This alternating pattern of reinforcement and cancellation creates an envelope, the physical, visual shape of the waxing and waning beat we hear. Translate this into a mathematical blueprint using cosine functions. Summing them and applying a trigonometric identity yields a new two-part expression. The second half represents the rapid pitch we perceive, while the first half is a slower frequency controlling the pulsing volume envelope. Mathematics perfectly predicts the experience, a continuous tone wrapped inside a slowly oscillating volume control. This leads to the ultimate formula for the beat frequency. The speed of the pulsing is exactly the difference between the two original frequencies. Subtract 9 Hz from 11 Hz, and the volume will throb exactly twice per second. Musicians use this mathematical difference as a highly precise tool for tuning. As a musician tightens a string, they shift its frequency closer to a reference note. As the gap between the two frequencies shrinks, the mathematical difference drops. This causes the beats to physically slow down. You can hear the math updating in real time as a rapid, frantic wobble stretches out into a slow, lazy throb. When the frequencies match perfectly, the difference becomes zero. The beats vanish, leaving behind one pure, steady note. The pulsing sound acts as a precise mathematical ruler, allowing human ears to align invisible waves of energy with total accuracy.